Let's get started. Again, another item that we have two grades. Yeah, okay. So now the people on Zoom can hear me too. So today we have again one of our own, Makrand Sinha, who's in computer science. He originally got his PhD at the University of Washington. Then he went to Amsterdam. I guess then he decided he really likes the West Coast, went back to Berkeley, and now he's somewhere in the middle between Berkeley and Amsterdam here. And so he's going to tell us about what he's doing about randomness, I guess.
All right. So hello, everyone. And I really thank the organizers for inviting me. And it's a pleasure to give a talk in this seminar and to tell you about some of the things I'm thinking about. So I thought it would be more useful if I talk about the broader direction. And that's sort of new. And there are a lot of exciting questions and things that we don't understand. And I work on sort of some aspects of these directions. And I will try to tell you about them towards the end. But I will also spend a lot of time highlighting what various other people have done in the field. So this talk is going to be about computational notions of randomness. So you might have an object that might have some structure. So you can look at it and figure out what the structure is. But if you look at this object through the notion of through the lens of efficient algorithm, meaning that if you only try to measure or do operations to this object with efficient algorithm, then this object will look totally random to you. It will look like complete noise. So this is, in a nutshell, what this talk is going to be about computational notions of randomness. How do we define them and what can we do with them? So one of the classical examples of such objects is what's called the pseudorandom generator. So it's a deterministic algorithm. It doesn't use any randomness. But if you feed n random bits to this algorithm, the pseudorandom generator, it sort of generates more random bits. It generates at least n plus 1 random bits. So you might think, how is this even possible? How can you generate more randomness from less randomness? And this is true. In fact, you can't do this in an information theoretic sense. And that's why this notion of computation comes in. So what you want out of this object is there is no efficient algorithm that can distinguish the output of this pseudorandom generator, these n plus 1 bits it outputs, from a truly random string. So any algorithm that any efficient algorithm that uses whatever this pseudorandom generator produces, it looks like a uniformly random n plus 1 bit string. This object, this particular definition was introduced in the 1980s, and it's been very widely used in computer science, cryptography, and so on. And today we are going to talk about sort of analogous things in the quantum setting. So quantum notions of pseudorandomness. And I hope there might be something here that might appeal to a diverse set of audience. So that's why I wanted to give this talk. So this talk will have sort of like 3 parts. The first part will sort of define some interesting objects, some interesting quantum pseudorandom objects. In the second part, we'll sort of look at some applications and some motivations behind why these objects were introduced. And again, they're pretty wide, diverse, ranging from quantum cryptography to quantum learning to sort of connections with physics. And in the last part, I'm going to talk about how do we construct objects, what assumptions do we need. And this is sort of, the last thing is the thing that I sort of think about, and I will talk about some of my works in that part. So, and at any time, if you have any questions, feel free to interrupt. So let me first introduce the real random objects that we're interested in, some properties that is good to keep in mind. So the first thing, the first random object is a high random state. is a quantum state on n qubits that distributed according to the Haar measure. So you can think of it as a uniformly random a vector on the two-dimensional complex unit sphere. So this is a very nice mathematical object. It's a lot of nice properties. It's been used everywhere in mathematics and quantum information. And let me point out some properties. One is that if you want to prepare this state, so if you want to start from all zero state, apply some quantum circuit, and prepare this state, this Haar random state, then with very high probability, you're going to need an exponential size circuit to prepare this state. So the state is very complicated and typically needs a lot of time to prepare. Useful to keep in mind is that if you take these n qubits and you divide them into two parts, give one part to Alice, other part to Bob, that Alice has, it has, in some sense, maximal entropy it can have. So if you divide the state into two parts, then how many qubits you give Alice if it was the smaller size. So with very high probability, these two things are true. Is a Haar random unitary. So it's on n qubit. So it's a 2 to the power n dimensional unitary raised from distributed according to the Haar measure of the unitary group. So again, you can intuitively think of it as a uniformly random unitary matrix. To implement this unitary matrix, so you want to build a circuit that sort of takes any input, and output of the circuit is the unitary matrix applied to that quantum state. With very high probability, you will need exponential size circuit to implement this unitary. Yes, of course. Yeah.
If I gave you a state,
yeah,
can you tell me that this is complex? I mean, this of this has this resonance.
Yeah, I think it's a difficult problem to tell. I think it's yeah, yeah, yeah.
Probably not enough.
No, yeah. I mean, I think you will get some answer to it in a. It's like, yeah, of course. Yeah. So that's a good question, and I hope maybe the later parts will answer at least some of this. Right. So these are very complex objects to prepare, and we want to sort of mimic these complex objects with sort of simpler objects that sort of essentially work in a similar manner. Let's use the first family of states that I will call pseudorandom states. These were introduced in a very nice paper by where they define what these things are, and they gave some constructions. So these are sort of families of states that they're indexed by some parameter n. It ranges from 1 to infinity, it's just a natural number. So you can think of for every n there is such a family, but I'm going to talk about a fixed n. And there are sort of several requirements to what we want out of these states. The first is that you want these states to be efficiently preparable. So if I give you an n-bit classical random input, that I will call a key, then there is some quantum circuit that takes these n bits, and it's sort of it's a polynomial size circuit, and then it outputs a state psi k. So in polynomial time, the state can be prepared if you know the key, and states are indexed by these keys. And the second requirement is that you want these states to sort of look random in some sense. And what I mean by that is no polynomial time quantum adversary can tell states that you just produced a truly Haar random state. And the adversary is just the algorithm. I'll call it adversary just to sort of make it clear that what it tries to do is this particular task. And the adversary gets these states psi k as input. It might use some SLS, and it outputs a bit that is 0 or 1. The adversary doesn't know the key that was used to prepare this. So the adversary only sees the mixture of all these states psi k, and you draw a key at random. So what you want from this channel that the adversary implements is that the output behavior of the adversary should be the same, whether you give it this mixture or whether you give it a mixture that prepares a hard random state, which the adversary doesn't know. So you don't want the so you want the behavior of the adversary, any polynomial size adversary, roughly be the same on these two things. Right? And another fact to keep in mind is that sort of this state here, if you sample a hard random state, and if you look at the mixture that it prepares, it's a maximally mixed state. It's just the density matrix, which has all the entries on the diagonal, they're all the same. So this is the maximally mixed state. So you want a mixture of efficiently preparable states that sort of looks like the maximally mixed state to any algorithm. And if you think about it for a second, what I've told you is sort of easy to satisfy. So we need some more conditions. So we need sort of some more properties of these states that we prepare. There are two properties. They're sort of not orthogonal. You can require one, you can require both. The first is that the state that you prepared is on more qubits than the key you used. So if you use n-bit randomness to sort of generate this state, you need, let's say, a state on n plus 1 qubits. This is what makes this task non-trivial. Using only n bits, you want to generate a state on n plus 1 qubits, at least n plus 1, that sort of look hard random. And the second requirement you can ask for is that even if the adversary A gets many, many copies of the state, any polynomial copies, then it cannot tell whether your state came from your pseudorandom distribution that you just chose, or whether it came from a truly hard random distribution. So basically, even if the adversary gets any polynomially many copies, the behavior of the channel on both these two distributions is sort of the same. Yes, Brian. Yes, I'm just going to address that point right now, but yeah. All right, so these are the requirements we want, either one or the second, or both of them. And you might think that the second requirement looks very similar to like a T-design. So what's a T-design? A T-design is a distribution on sort of pure quantum states whose Tth moment, where T is some number, as parameter, is sort of exactly equal to the hard random state or approximately equal to the hard random state. So this is what a T-design is. But so for T-design, you fix the parameter T. So you fix like n or m squared copies, and then you prepare such a T-design. And then you want all the moments up until the Tth moment to sort of look the same. And here, the definition is very similar, but here this needs to work for all polynomials in T. So you can't fix a T. So if you can actually generate a super polynomial T-design where T is super polynomial, then you would satisfy this requirement. But the point is that you can't generate a super polynomial T-design in polynomial in N, because it's an information theoretic notion, it's not possible. This is where the computational part comes in. So in a sense, you generate something that looks like a super polynomial T-design efficiently. So I hope that answers your question. Yeah. All right. So these are like these families of states. And this first notion, this specific notion was introduced in this paper by Morime and Yamakawa. This simpler requirement, but it's also sometimes very useful. Yeah. Well, I mean, it has some applications. Maybe we will see it later in the talk. But I mean, this is saying that even if you want just a single copy, how do you make it non-trivial? Because if it was a state on n qubits, then you can generate like sort of sample n random bits, just prepare the maximum mixed state. I mean, it's trivial to prepare. I mean, it's exactly the maximum mixed state. But if you want to use n random bits, can you prepare something that looks like the maximum mixed state? So that's non-trivial. All right. So the next object I'm going to introduce are what's called pseudo-entangled state. These were introduced in this nice paper by Giorgio and Hoban, and they were generalized and refined in these two papers by Aronson et al. And Bullen et al. And again, these are a family of states. The first two requirements are the same. You want to efficiently prepare them, and you want them to be indistinguishable from a higher random state. But what a condition out of things is that if you sort of break the state you generated into two parts, give one part to Alice, one part to Bob. So if you look at the entanglement entropy across any cut, then it's sort of small. So if you look at the reduced state that Alice gets, that Bob gets, the entanglement entropy is sort of log square n across any cut. So you can choose any cut you want, and the entanglement entropy. And what this means is that you cannot distinguish this state that you just produced from a higher random state. But a higher random state has, in some sense, maximal entropy. So if you divide the state into two parts that are roughly equal size, then it will have linear entropy in the size of the parts. Here, we're saying that the new state you produce is very, very small entropy, but you still cannot tell the difference from a higher random state. So this is the second notion of quantum pseudorandomness that we're going to look at. And let me mention some other remarks is that here we are looking at distinguishing the state psi k from a higher random state. And you want to say that these families are indistinguishable in some sense. These leads to sort of stronger notions of pseudo-entanglement. And there were some other notions that were also recently considered, some more operational notions by Arnaud, Friedman, Buckersky, and Vidic. But I'm not going to go too much into it, but if you're interested, you should take a look. So K is n bit key. So you basically want to generate, like, for any fixed n, you want to generate like 2 to the n states. Sorry, I didn't get. Well, apparently, yes. Yes. Yeah, the entanglement is like not very low. It's like still like logs. I mean, it has to be like super logarithmic. So yeah, exactly. Right, and the last family I'm going to introduce is some pseudorandom unitaries. Now these are unitaries. And again, you want something very similar requirement. The first is that you want these unitaries to be efficiently implementable, meaning that if I give you a key, you can generate a circuit that implements this unitary. It takes a key, and it sort of takes any quantum state as input, and it applies the unitary UK on that input. So you want the efficient circuit that implements this unitary. Again, these were introduced in this paper by Giulio and Song. And the second requirement is sort of, again, very similar to what we saw. So I hope this comes naturally, is that no efficient quantum adversary can distinguish the behavior of this unitary that you just prepared from a truly higher random unitary by making queries. And what this means is that if I prepare a quantum circuit where you start with a quantum state, you apply some gates, and you use these UK gates somewhere, and then you output a 0 or 1, then there is no efficient quantum circuit like this that has the very different behavior on this thing versus when you replace these UK gates with a truly high random gate. And the last thing I want to point out is that sort of these pseudorandom unitaries are very sort of powerful objects. You want the output behavior to sort of look the same for any input state. So there are sort of uncountably many input state, and so in this very giant Hilbert space. And in particular, if you just fix this input state to be the all 0 state, you will get like a pseudorandom state. So if you have the pseudorandom unitary, you can prepare pseudorandom state. And you might also be able to prepare pseudo-entangled state, but not 100% sure about that. Yeah. So those are sort of the family of some interesting family of objects that we are going to look at in this talk. So again, there are more objects that have been introduced, but I will stick to these. So that was essentially the first part of the talk. So let me tell you why people introduce these objects, so that you get some sense of motivations behind them. And I think this is where people from different fields would contribute a lot, because as computer scientists, we don't know what potential applications of these objects. So we're going to look at some applications to different fields. So let me first start with sort of cryptography. And in particular, this one particular cryptographic thing that we want to do called commitment schemes or bit commitments. So again, I'm not an expert in cryptography, so I'll just tell you what this means on a very high level. So you have some sender that has a bit in mind that he wants to send to a receiver. And sort of commitment scheme has two phases. In the first phase, the sender sends some message, a quantum message possibly, to a receiver. And what you want is that after the sender sends this message, he cannot change his mind. He cannot oh, I had a different bit in mind. And so sort of you're basically imagining this as the sender sort of takes his bit, puts in the box, locks the key, and then sends it to the receiver. And then he cannot change what was in the box. And in the second phase, what you want is that the sender sends a key to this box. And when the receiver gets this key, he can open the box and he can look at what the sender wanted to send. Before the receiver gets this key, he cannot really tell what the sender wanted to send. So this is what's called the commitment scheme. And it's a very classic object. It's been around for a long time. Interesting applications that I'm not going to talk about here. So now, how can you use pseudorandom states to build such a scheme? And there was a sort of here, the sort of, if the sender wants to send a 0 bit, then he prepares this state, which is a uniform superposition over all sort of over all 2m plus n bit strings. And then he prepares this state psi k, and he appends it to this state. If the sender wants to sort of send a bit 1, then he does the same thing, but he applies this poly operator x to the r and z to the s. So if you don't know what they are, it's not too important for this talk because we're going to stay at a high level. But these are the quantum one-time pad. It applies the quantum one-time pad to the state. And psi k is a pseudorandom state on 2n qubits. So it's just a single copy of a state, but it's on more qubits than you start with. And now sender sends this second register that contains the pseudorandom state in the first phase. And now before, now the sender hasn't sent the key. So the key will be sort of the sender sends all the other registers. So before the sender has sent the key, if you try to distinguish these two states, they will look the same, because in one case it's the maximally mixed state, and in the other case it will be a mixture of pseudorandom states you prepare, and sort of that's what we want out of them, that no efficient algorithm can sort of tell them apart. This is one sort of example of application in cryptography. There are several others. You can build out of them. Yeah. Okay, that part is more technical. You have to ask, okay, what does it mean the bit can be? If basically the receiver should be able to detect that the bit can be changed, and there are different notions. So it works for some notion of that. So yeah, so that I'm not going to talk about here. Also, that part really, yeah, has That's not where the pseudorandomness property is used also. So yeah.
That's the question. Receiver does take the receiver.
The receiver what? Yeah, in the second phase, the receiver gets that. Not in the first phase. Not in the first phase. Yeah. Yeah, you had something to add? All right. Maybe we can talk about it later. So Rakshita might be able to tell you what happens to this thing better than I can. So. All right. So that's a commitment scheme. Let me give you another example in quantum learning. And this comes from in this very nice paper by Huang et al. I think the paper title is Quantum Advantage in Learning from Experiments. And so there's this one particular task, quantum PCA, which they considered in this paper, where you have an unknown n-qubit mixed state. You know that the top eigenvalue of this state is sort of constant and is greater than all the other values by a constant factor. And you want to predict the output of some observable on the top eigenvector. And now in this paper, what they're interested in is sort of distinguishing these two scenarios. The first they call a quantum enhanced scenario. Here you get multiple copies of this state, and you can perform on all the copies simultaneously. And the second thing they call a conventional scenario, where you prepare the state, you measure it, and depending on the outcome of the measurement, you prepare another copy, and then you do some other measurement, and so on. So here you can only do single copy measurements. On the left, you can do multi-copy measurements. In fact, in this paper, they ran some experiments on, I think, Google Sycamore to sort of distinguish these two, to demonstrate quantum advantage in between these two scenarios. For some tasks, I'm not sure they did it for this particular task, but for some other tasks, they did it. So what they showed in this paper, what they proved is that for the task on the left, you can do it with just constantly many copies of the state. But on the right, even if you can prepare this state in polynomial time, you would still need like super polynomially many copies to sort of do the same thing with roughly the same amount of error in the scenario on the right. So this is what the result and sort of how do pseudorandom states come in. And the family here, the family of hard examples for which you can't do this is actually based on pseudorandom states. So using these pseudorandom states, you can build the family of efficiently preparable states that you sort of that look almost hard random, and you can't sort of do these sorts of things. So this is a second example in quantum learning. There are many other properties here for which pseudorandom states are very good candidates. Many other property testing questions that, yeah. About this task. Well, I think maybe you should ask people who work in physics, because I think they care about this part. So, yeah. Okay.
I think the intuition here is abstraction and the idea if you have a bunch of variables in, and you benefit from collecting all of them and doing some single kind of global operation on the measurements. And so the idea is in physics, we're trying to learn something from a bunch of measurements that never makes sense.
And also, I think, as far as I understand, multi-copy measurements are difficult to perform experimentally. So that is one motivation behind this. So I think they have some interesting experiments, not for this quantum PCA task, but for some other tasks. So you can take a look at the paper if you want. Yeah, I mean, I can believe that. All right. So the next example is sort of related to sort of condensed matter physics and Hamiltonians. And it's about learning entanglement structure. So this is a very simple toy example that they show. So suppose you have n qubits on a line in one dimension. And this is from this paper by Boolean, Pfefferman, Ghosh, Medkar, Vazirani, Zhang, and Zhu. So they basically construct two families of Hamiltonians. One, the Hamiltonians on this n qubits, hk and h prime k. And these Hamiltonians are sort of local. I mean, the locality is not constant, but they're log and local. And there is some spectral gap. Both are spectrally gapped. You can, the K here is a key. So you can sample a random Hamiltonian from either of these classes efficiently. And still you can't tell them apart. So I haven't told you what it means to not be able to distinguish Hamiltonians. And I don't want to go too much into it, but what you can think of it that you can get the description of these Hamiltonians, you can prepare their ground states, but you can't do any operation on them, so that you can tell where your Hamiltonian came from. And the last point is that the ground state of the first Hamiltonian has near area law entanglement, but the ground state of the second Hamiltonian has sort of volume law entanglement. So what this means is that if you look at the ground state of the first Hamiltonian HK, and you divide it into two parts, and you look at the reduced density matrix, the entropy is sort of polylog n, where I think you should think of it as log square n or log cubed n or something. But on the other hand, for the second Hamiltonian, the entropy is really like some constant times n. The area law entanglement, that's what it means. And the second case, the entropy is very high, so which is volume law entanglement in this 1D. And I think they prove similar results in 2 dimension across some cut. So, but you can take a look at the paper if you want. And I think there are very interesting questions about, can you make this more physical and more sort of connected to Hamiltonians you see, like in physics and so on. Yes. Yeah. Yeah.
What about this? This operation is more expensive than I would think for sort of low. For low entanglement states, I would actually think it would be.
Yeah, the entanglement here is like super logarithmic. That's why you can't do this efficiently. So if you want to do this, you will need like super polynomial. Yeah. Yeah, if your entanglement was sort of log, then you could do this. But yeah, it's sort of super log, so yeah. Right, so again, this sort of things, examples they build out of pseudo-entanglement, sort of pseudo-entangled states. In fact, sort of these more general states. And basically, the message here is that somehow the ground state entanglement structure is sort of hard to learn in some sense. And the last example, okay, I will be sketchy about it because I don't know much about it. So about black holes and quantum gravity. So black hole dynamics sort of look like a Haar random, so unitary Haar random unitary to an outside observer. The black hole are supposed to be the best scramblers of information. So if you throw a black hole and let it evolve, it will look maximally mixed. So a lot of papers in physics model it as a Haar random unitary. But this is not really realistic because a Haar random unitary is sort of takes exponential time to implement. So how can a black hole do a computation that takes exponential time to implement? So many papers recently have tried to use sort of model a black hole as a pseudo-random unitary. And then they try to, I guess, figure out various paradoxes about black holes using these objects. And sort of the second thing is related to quantum gravity and this ADS-CFT correspondence. And in fact, this was pseudo-entanglement, was that sort of there's this ADS-CFT correspondence where there's a theory of gravity in some space, and you map it to quantum mechanical theory through some dictionary so that you can take observables and states in sort of quantum gravity space. You can map it to quantum mechanics. And there was this very nice paper by Boole and Pfeffer and Vazirani, where they sort of argued that this dictionary is exponentially complex. It would require like exponential size quantum circuit to implement. And which would be sort of surprised because this would mean that there is some physical process that you can't even implement the quantum circuit efficiently. So and there were several follow-ups. Let's try to explain that this only happens inside a black hole. It cannot happen outside a black hole. Outside of a black hole, this is easy to compute and so on. So one of the motivations was to sort of really construct states which hide their entanglement structure and somehow argue that this dictionary, the complexity really originates from states being able to hide their entanglement structure. So that's one of the motivations behind it. And I'm not sure where we are at this, how far we are from fulfilling, from saying something like this, but that was one of the original motivations behind it. Right. So that's some applications. Hopefully you can find some more because I'm sure there are many more. And let me talk about how do we build these objects, what assumptions do we need to build them, and so on. So, I mean, it's very easy to come up with candidates to build these objects. First candidate is a random quantum circuit. So you have a quantum circuit. You choose these gates randomly from some fixed gate set, universal gate set. And the circuit has polynomial depth and polynomial size. And in fact, we already know that these circuits are sort of like poly and approximate designs in some sense. This looks like a very good starting point. You can conjecture that, okay, random circuits of poly and depth, they give you a pseudorandom unitary on n qubits. And I would believe this. And in fact, if you apply it to all zero state, you would also get pseudorandom states. So this is a very nice conjecture. You would think that we can actually prove this from, since we know something that looks very close. But actually, maybe in complexity, we sort of prove a statement like this and we pull up our hands. It's like if you can prove this without any assumptions, then this would imply something like P is not equal to NP. So I say something like because I don't want to get into what specific complexity classes you're showing are not equal, but this would be a very hard task to do from the current state of knowledge of complexity theory. So we sort of say that, okay, we can't prove this without any assumptions in some sense. All right, so what sort of assumptions can we make and how can we build these pseudorandom states? And let me tell you this very interesting sort of thought experiment by Impagliazzo, who tried to sort of classify different assumptions according and sort of gave names to the world we live in if those assumptions were true. And there are 5 worlds he came up with this that sort of captured the majority of the assumptions. And sort of let me go from the right to the left and try to tell you what the assumptions are. The world on the right, pick up. This is the world where P is equal to NP. So this is the world where you could solve any NP complete problem like SAT with a classical algorithm very efficiently. You could use computers to write poetry for you or do whatever you want. So this world is a computational utopia in some sense. The second word is sort of world is heuristica. Here P doesn't equal to NP, meaning that there are instances of the problems you want to solve that you can't solve, but they're not typical instances. Typically, any problem you encounter in the real world or on average, they're easy. So basically, P is not equal to NP in the worst case, but on average, problems are easy. This is called heuristica. And the word in the middle is like the worst of everything. So I'm not going to talk about it because it's a little bit depressing, but it's called pestilent just from the name. So in these 3 worlds on the right, the basic premise is that you can't do any cryptography either. So you have a computational utopia, you can solve problems you want easily, but you don't have any cryptography because cryptography is somehow sort of based on the existence of hard problems. And the word on the 2 words on the left, they're called crypt. And here, cryptography exists. I mean, in minicrypt, you can't do all sorts of cryptography, but you can still do a lot of it. And the word on the right, you can do sort of most cryptography. And one of the most basic assumptions you can make for cryptography is sort of the existence of one-way functions. So these are functions from n bits to m bits that you can easily compute. So if you take any input, you can easily compute what the output is. But you can't sort of go back. So you can't take the output and try to find, okay, here is one particular input which sort of gives you that output. For instance, you can think of factoring. I mean, it's very easy to multiply two very long numbers, but it's very, very difficult to find a factor of a very large number. And that's what sort of all classical cryptography sort of pays out of, I think, a majority of it today. And in fact, this is sort of a necessary and sufficient condition for most cryptography. So you can build most objects out of them, and most cryptographic objects you build, they sort of imply that one-way functions exist. So this is sort of assumptions that you may want to make if you want to show that cryptography exists. And for mini-crypt, you sort of assume that very structured problems like factoring are still easy, but one-way functions exist. And cryptomania, which is probably where we all live in, is the world where factoring is hard and one-way functions exist. So you can do a lot of cryptography. So these are sort of how you can classify different sort of assumptions you can make. And if P is equal to NP, then one-way functions don't exist, so you can't do any cryptography. So now how can you construct pseudorandom states? And to construct them, there is a very simple construction that I can tell you, and it's based on these certain objects that I will call pseudorandom functions. So assume that you have one-way functions that even a quantum computer cannot sort of figure out. Then you can efficiently construct what's called the pseudorandom function family. So these are functions that map n bit to 1 bit. They're indexed by some key, and they look totally random, so to any algorithm. No algorithm can tell whether this function is a totally random function that looks like this, or it's a function from this family. And so this is what it means. If you draw a random function from this family, it sort of looks like a totally random function to you in a computational sense. And now this theorem, so this construction was proposed by Ji and Song, who analyzed the worst versions, some more complicated version of this construction. And this was proven by Brakersky and Shmuley. This very simple family is a pseudorandom state family. And what is this family? You just have phases that look like -1 to the power whatever this function outputs. So you basically have a uniform superposition with some phases, and the phases are +/-1, and they're given by applying this function on your input. And how do we show that this is a pseudorandom family? I mean, the first thing is you replace this pseudorandom function with a truly random function. And you can sort of assume that no algorithm can tell apart these two things. And this approximate C means that they look the same to any computationally bounded algorithm. So you can replace it by a truly random function here, just by our assumption. And this is secure against such algorithms. And the second part is sort of just purely information theoretically showing that these two, that if you replace this by a random function, the states you get look the same as a hard random state. Yes, Felix, yeah.
That means that it's hard to
Yeah, but yeah, so this is not obvious how we can construct them, but there is a way to construct such objects starting from just a one-way function.
Q is like a sufficient. Like if you have that, then you construct a pseudorandom family.
If you have a one-way function, you can construct a pseudorandom family, and if you have a pseudorandom family, you can construct pseudorandom, one-way functions also. At least, yeah. So in the classical world, you can do it. Quantum world, I'm not 100% sure what exactly is needed, but I mean, I suspect, yeah, they're probably equivalent. So. Right. So yeah, usually in a lot of these proofs, you start with some cryptographically hard family, and then you replace it by truly random family. And then the difficult part is to actually showing that the information theoretic part is to show that these two families are sort of close in an information field. If you construct states where you have +/-1 phases uniformly at random, then they sort of look essentially like a hard random state. You can take even like exponentially many copies then, and it will look very close to a hard random state. Okay. Right. So basically, if we assume one-way quantum secure one-way functions exist, then we can show that pseudorandom states exist. So they exist in these two worlds. And so now you can ask, okay, are one-way functions actually necessary to do quantum cryptography? Because there are some tasks which are like key distribution, which you can do without any assumptions even in a quantum world. But unfortunately, that's not true for most quantum cryptography. You still need one-way functions to do them. And in fact, what we showed with Kretschmer-Kianen et al. Is that pseudorandom state exists even in this algorithmic world. So even you assume even P equal to NP, then there's still some cryptographic assumption you can make that is independent from this question, under which you can construct pseudorandom states. So essentially, what it means in a nutshell is sort of these states are a weaker assumption than one-way functions and quantum secure one-way functions. So you can do quantum cryptography and other applications, even if one-way functions do not exist. So again, there's an asterisk here because it says terms and condition apply. So I'm not going to precisely be able to tell you what this is. It will take too much time. And we only prove this for single copy pseudorandom states. For multiple copies, we can prove it under some conjectures, but that's what it means. Okay. So that sort of tries to clarify what sort of assumptions you need and to construct these states and whether you need one-way functions. And in fact, you can also construct pseudo-entangled states from some sort of cryptographic assumption. But I'm not going to talk about it here. But I'm going to talk about pseudorandom unitaries. So can we construct them from pseudorandom, any kind of cryptographic assumption? And because pseudorandom unitaries are a very powerful object, they work for all input states. So if you can build pseudorandom unitaries, you can also build pseudorandom states. So they're very difficult. And up until recently, all we had were really conjectures that something is a pseudorandom unitary. But recent works by Liu et al. And Anant et al., they sort of made progress that if you only restrict yourself to applying the unitary and product states, you can show that it's pseudorandom and so on. And in fact, very recent work from last week with Medgar, Poremba, and Yuan, we sort of make slightly more progress in this question. We sort of construct pseudorandom unitaries that work against all non-adaptive polynomial time algorithms. And let me try to tell you what this means. So what are non-adaptive algorithms? So non-adaptive algorithm, you can feed it any input state. It does some computation in the beginning, and then it applies the unitary in a single layer. So you apply column element layer, and then you produce some output. And again, this circuit is efficient, so all the other gates apart from the unitaries are sort of, you can efficiently implement them. That if you replace these unitaries with a truly hard random unitary, then these two channels sort of look the same on any input state. So this is what it means. And more mathematically, if you apply this channel, which is UK tensor identity, let's say the first layer is the identity, just to simplify notation. If you apply this channel UK tensor identity on any input state, and if you don't know the key, the sort of the output sort of is indistinguishable from this other channel where you apply truly hard random. Okay. So this is what it means, and let me just tell you the construction, and then we'll pretty much end. So construction is very simple. You have a pseudorandom function family, and let's say you construct this diagonal matrix, which applies -1 to the f of x. Okay, you take any input state x, and you apply it. You give it a phase basically. And then similarly, you construct a pseudorandom function family from one-way functions. So this is a family of permutations that take n base to n bits. You basically take any computational basis state and apply the permutation on these n. And then our construction is basically this. You take like an n-qubit Clifford unitary, uniformly at random. You sample a function, pseudorandom function from this. family uniformly random, and you build this operator, and then you sample a uniformly random permutation from this family, and you take a product. And we sort of show that no, this looks like a random unitary to any non-adaptive algorithm. In fact, we conjecture that this is a pseudorandom unitary, but we can't prove it. And I can't show you the proof, but it's just there's a lot of calculations using computation theory sort of argue that. So some sort of yeah. So the P and F are classical. So you just build they're in the computational basis. Yeah. Basically. Sorry. There's Clifford with just Clifford circuits. I don't think can be pseudorandom. You can learn them, I think. I'm not 100% sure whether you need some sort of inverse. Yeah, basically. PFF are based from this assumption that they're quantum secure Monroe functions. Okay, so since I'm running out of time and we're pretty much at the end, let me just end. So basically we defined some interesting pseudorandom objects. We looked at some interesting applications, and I'm hoping you can find more. And talked about a little bit about what assumptions do we need to build such objects. And there are many interesting directions. We want to relax the assumptions. We want to construct pseudo unitaries that all. We want to construct more pseudo physical, and there are many interesting questions that remain. And I hope you might be interested in thinking about them. So thank you very much, and let me end here. Yes.
You mentioned random states, right? So does that mean in some of one-way function, quantum state, having these one-way functions that right? That I mean, if you have pseudo-random paths, you can do some quantum paths to create pseudo-random states.
Yeah.
But now you can bypass that and do this directly. Quantum algorithms, which before you can do, or
I'm not sure with applications. I'm not sure of any applications yet, so that's an interesting question. Yeah, in principle you can do that, but not sure there are any interesting things.
There was another one there.
Yeah.
Yeah, you mentioned that there's this conjecture that sort of goes through the breaks of complexity theory assumptions that you have random gates. But is there a consensus on sort of whether the belief is that conjecture is right or not? Forgetting about proving it, is it why we believe that that's true, or?
Well, I would believe it. I mean, yeah. So I mean,
you say there's community consensus, sort of.
Well, I'm not sure. I guess I haven't done a survey, so I can't tell what other people say, but I would believe it. Maybe the weaker conjecture, whether you apply to all zero state and then that produces pseudorandom state, that I would more strongly believe, probably. Yeah.
Hey, further questions? All right.
Yeah. With classical operations, so I think there might be a question here also. I think you probably, I mean, these are in some sense quantum objects. So, I mean, I would guess you need some kind of classical gates to do it. Because otherwise, if you're always in the computational basis, then you can measure, and you would, with probability 1, you would get to see something in the computational basis. Right? So you can actually tell them apart from a high random state. So I think you would need something. Yes, Paul.
So this is going to reveal my total misunderstanding of everything. If you want to make a state in some random, a single qubit, randomization.
Yeah.
It seems like you can do that with very simple gates, but that has an exponential amount of complexity in like what angle I'm rotating about and what and how the axis of the rotation and how much.
Yeah.
So it seems like you can do it with classical, some exponential amount of classical randomness, and then a very simple piece, as opposed to needing some exponential number of quantities.
I think what you're right, but I think all these statements I'm making, they're in the asymptote when you have many qubits. So and the statement is like no algorithm can distinguish them in polynomial time or some polynomial in n. So as you increase this time, and you would the assumption is that if this time gets very large, then you can't tell whether you get a computational basis state from a truly hard random state. And I think so that assumption would be broken if you could do this. So, yeah.
Okay. Any further questions? If that's not the case, let's thank our speaker again.